Start a little bit on this topic called graph theory, okay? So graph theory is a very interesting topic. And, basically what a graph is, it's just a bunch of vertices, okay, which may or may not be in like a plane, and they're connected to some other vertices. So and these are called edges. This is like an edge. And like edges could be kind of weird. There could be a double edge, there could be a loop to itself, okay? And essentially, what graph theory to me is, it's kind of an interesting place to do combinatorics. So it's almost like graph theory is rich enough to capture. So just as a number theory is kind of an interesting place to do logic. Like number theory is rich enough to capture basically all logic. Graph theory is interesting enough to capture basically all the combinatorics I can think of right now, at least. But yeah, so it's enough to capture a lot of combinatorics. Okay, so you can think of it maybe as like a systematic way to do combinatorics, or like you don't it's the theory of combinatorics in that you don't have to kind of be clever every time to solve a combinatorics problem. You might be able to relate it to a graph theory problem you've already solved. Okay, and it's kind of famous for being very easy to understand, and it could create quite a lot of difficult problems. Okay. One problem that's kind of interesting that made headlines, well, not completely recently, but in maths terms very recently, was this Hadwiger Nelson problem, okay? And what the problem essentially was it asked you if you could color in points in the plane. So if you had a plane, okay, like could you color in the points? So like maybe this region had this color and this region had another color, okay? Such that any 2 points which are unit distance apart, okay, had different colors, okay? And um, so it was quickly, this was like 60 years ago, this person proposed, these two people proposed this problem, and it was quickly found that 7 colors could be done, okay? So if you could tile the plane, it was, I don't really I don't really want to show it to you right now, but the point is, if you tile the plane with hexagons or something like that, with 7 colors, you could achieve a tiling where any 2 points would have different colors. Okay, so 7 colors is enough. Okay, and that's a nice little proof. Maybe I'll show you if people are interested. Um, and there's some obvious calculations. Maybe it shows that 3 or less is not enough. Okay, so the aspect of this problem that survived was um, whether 6, 5, or 4 is enough. Okay, and you could find this on YouTube a little bit as well. I'm pretty sure. And the thing is, recently, so in 2018, someone showed that um, 4 is not enough. Okay, and the way they showed it was they produced a planar graph. Okay, so some points which can be put and some edges which can be put on the plane, and the edges are only joining points that are one distance apart. Okay, so he produced a graph. So this graph would be a subset of this plane. Okay, so if every 2 points in the plane satisfy this property, then any two vertices on that graph should also satisfy that property on any graph that you make. Okay. And what happens is, okay, that with this graph, okay, the graph was not able to be colored no matter how you tried with four colors. Okay. So that proved that four colors could not be done to color the whole plane either. Okay, so this was interesting, especially because De Grey was like some kind of biologist. He's maybe just a smart guy. So this is kind of like you guys, right? You don't know necessarily that much about maths yet, but you definitely can understand these problems, and with maybe a little bit of ingenuity, you can come up with some solutions. Okay, so this is why this was particularly interesting. It was like a non-professional mathematician, probably just a smart guy, came up with this example. Okay, and the example is kind of interesting as well, because at first the first example he came up with had like 20,000 vertices, so 20,000 or so vertices. Okay, so if you measure the simplicity of the example by the number of vertices, 20,000 might seem like a lot. Okay, and it's not actually like a computer you think could handle that. A computer would not be able to handle that very easily because you have to do all the combinations. That's the whole point, the combinatorics, right? But the one thing that was nice about the example is you only had to check it for a bunch of like a few hundred vertices. Okay, but nonetheless, you had to use a computer to check the answer. Okay, so that's a lot different than sort of some of the other kind of proofs that we've been accepting. Okay, and then sort of just like how when we solved those problems before, we kind of tried to make the examples easier. Okay, just like in JA1 we just did. Okay, and then started a question of, well, what's the smallest example we can have? Okay, so what is the smallest example? Or like, what is the example with the smallest number of vertices? Okay, and so this kind of was interesting. It started what's called like a Polymath Project. Okay, though I don't think the spirit of the Polymath Project has been actually met yet. Um, what it essentially is just a huge online collaboration with like, it's kind of like a forum where everyone just contributes their little bit until the problem gets solved. And this is the kind of problem that lots of people can work on, even though they might not understand anything. Okay, but I think the problem is when some people know too much, they end up being the only ones that work on it, and then it becomes just a normal project. But this is interesting because this is something that you guys might get involved in. This is something that only existed in the last 10 years. Okay, this kind of polymath idea. It's kind of ironic because polymath means someone who's basically good at everything. Okay, and the project is essentially trying to enlist people that are not good at anything. Okay, so it's kind of ironic. But the idea was to get tons of people who don't know anything and contribute that little bit. Okay, and in some ways we're all like this. Okay, we don't really know anything about graphs that much or other areas of maths, but we can understand this problem. Okay, and I want this to be a guiding problem for how we're learning graph theory. So so I think even before this project started, the author was able to get it down to like 1,500 vertices. Okay, and some other people, I think this person called like Martin Huel or something, I don't know. He managed to get it down to in the 500 vertices. And so since 2018, like the 2 years since then, I think they've gotten it down to 510 vertices. Okay, and still the solution cannot be checked by hand. Okay, so there's still a little cluster that you need to check with a computer, and which in some ways is not mathematics. Okay, um, at least not how we traditionally like to know it. So if you want to kind of think about this as you learn graph theory, it might help you motivate. One motivates the other. Okay, so there's lots of open questions here. So for example, what is the lowest number of vertices? Yeah. So and maybe open questions are nice to talk about right after a test where you didn't solve all the questions, because these are questions that no one's solved yet. Okay. Examples with less vertices. Okay. For example, it's known that if you have 12 vertices, you can't have an example. For example, so if 12 vertices, no example is possible. Okay, and the question might be is like how much higher than 12 can this can you prove it? Can you prove it from the other direction? So instead of going down from 510, can you show that say 13 is not possible? Okay, and even if it's not known right now, it might not even have a nice argument. Okay, even if it is known for the 13 vertices, it might not have a nice argument. So this thing in maths, remember, we're not just caring about knowing stuff anymore. We actually want sort of nice arguments. Okay. And obviously, there's examples that are, the question is, can it be done with 5 or 6? Yeah. And then we know that for 6 colors, so any graph with less than 6,000 vertices can be colored with 6 colors. Okay. So to find an example that can't be colored with 6 colors, you have to look for beyond 6,000 vertices, which is a bit of a warning. Okay. Okay. So I'm starting to repeat myself too much now. Um, so basically, I guess it would be really nice if there was an example that 4 colors was not enough, which could be checked by humans. Okay, so that'd be a great thing, and that's something like you guys can even think about. Okay, because this is basically you're kind of at the same level as, well, maybe a little bit less maturity than this guy who came up with that example, and and I guess no one had done anything for like 60 years, and so this made the headlines for a little while. Okay, so with the seniors, I guess I want to go backwards from graph coloring, and with the juniors, I want to go forwards from the basics of graph theory. Okay, so maybe you can keep this problem in mind. If you can come up with some solutions to these problems, we can work together and we can sort of um, discuss it and stuff. And who knows? You might make a breakthrough. Okay, so it's something very fun and motivating to think about at your age. So it's not you're just learning stuff that's been done ages ago. Like sometimes you can be at the cutting edge of sort of graph theory research um, before you know it. Okay. All right. So let me just start with the PST stuff now.